armed with all of this information that we've spoken about today, it's really exciting to see all the advancements, both in current missions, but also planned missions, as we begin to build this infrastructure and move the field forward. There are many design considerations and trade-offs to think about, but each of these missions really kind of takes a further step forward. And so you can see here an overview of some of the missions, both current and planned, that they're tackling different link directions, right? Uplink and downlink, tackling different orbits, as well as optical system design, optical ground station design, and different assets for communication, both with satellites and other airborne assets. These are all problems that need to be tackled, and it really shows the advancement of the field and how promising this technology is. And you're seeing investments kind of globally from different space agencies and different entities and organizations to really move this technology forward. So really exciting time to talk about this technology. I did want to kind of end with an overview of some of the missions and kind of point out some highlights and differentiating features of what makes them interesting, what is moving the field forward. So we can start with the Chinese satellite launches, some of the first demonstrations that this is actually doable, this is possible. And they're continuously planning new launches as well. Something for me that sticks out is the ability to actually do entanglement-based protocols. So you can see in the Messier satellite, they were able to demonstrate Eckert 91, which is entanglement-based. So that's really a critical advancement in the field, that this is doable. We can in fact distribute entanglement from a satellite. So that's a massive kind of step forward for the field. They're also working towards daytime operation for QKD to prove that this can be done during the daytime, and in spite of all the solar effects that we spoke about today. And these slides are available for download, so I'm not going to go too deep into the details here. Just kind of wanted to focus on some of the distinguishing features and properties of these different missions. So in Europe, in the EU, so the European Space Agency, they have a few satellite projects going on: Cube 1, Cube 2, Eagle 1, Saga 1G, Iris, in parallel to all of their terrestrial fiber infrastructure, the Euro QCI effort that is going on. So it's really exciting to see all they're doing in Europe, both on the ground, on Earth, but also in satellites. Something that sticks out here for the European efforts is that they are implementing a variety of wavelengths here. So some centered around 850 nanometers as well as 1550. So each of these missions, really helps to understand the effects of these different wavelengths, to navigate this trade-off landscape that we touched on today, but also with the vision that Europe has to connect a variety of optical ground stations across Europe. So this is really the kind of angle they're working towards, and I think it's a really promising strategy. Something that's very exciting also from Canada is the QEYSSat project. And for me, the exciting thing about this is that they are pursuing both BB84 and BBM92 protocols, so prepare and measure and entanglement based, which is really exciting. So creating a system that can support both of these protocols, but also, as Suparna mentioned, most of the missions were considering downlink transmissions, and QEYSSat is going to move the field forward in terms of uplink configurations as well. So a really exciting time to be learning about these systems and keeping an eye on all the advancements and what we can learn.